Every time you look at a new smartphone, the marketing teams scream about megapixels. 50, 100, even 200 megapixels packed into a tiny glass slab. But in the world of high-end industrial imaging, there's a sensor that ignores the hype entirely. Meet the Sony IMX785. On paper, it looks like a relic from 2010 with just 5.12 megapixels. But don't let that number fool you. This sensor is designed to see things that your flagship phone literally cannot perceive. The secret isn't how many pixels it has, but how big each individual pixel is. While consumer cameras are shrinking pixels to the size of bacteria, Sony went the other way, and the physics behind it is absolutely brilliant. Imagine trying to catch rain with thousands of tiny thimbles versus a few dozen large buckets. In a downpour, those thimbles fill up and overflow instantly, creating a chaotic mess. That's exactly what happens when you chase high resolution on a small sensor. In sensor terms, this overflow is called electronic noise. When pixels are too small, they can't distinguish between actual light and the random heat of the camera's own electronics. You get grain, artifacts, and muddy colors. The IMX785 solves this by giving every pixel room to breathe. By prioritizing the physical surface area of each light-gathering site, Sony has created a sensor that treats every single photon like gold. To understand why this works, we have to look at the pixel pitch. This is the distance from the center of one pixel to the center of the next. On the IMX785, that distance is a massive 2.9 micrometers. For context, many modern smartphone sensors have a pixel pitch of less than 1 micrometer. That sounds like a small difference, but because we're talking about area, the IMX785's pixels are actually several times larger in surface area. This isn't just a design choice, it's a fundamental embrace of mechanical physics. More area means more photons, and more photons mean a stronger, cleaner electrical signal before the computer even starts processing the image. The real magic happens when we talk about full well capacity. Think of each pixel as a capacitor that stores an electrical charge generated by light. The bigger the pixel, the more charge it can hold before it saturates. If a pixel saturates too quickly, you lose all detail in the bright parts of your image. The highlights just turn into a flat white blob. But the IMX785 has such a high capacity that it can capture incredible detail even in blindingly bright conditions. This high capacity also means the sensor can stay open longer without blowing out the image, allowing it to collect more data and produce a much higher signal-to-noise ratio. It's the difference between a whisper and a shout. So we have a sensor that ignores the resolution race to focus on pure photon efficiency. It's a bold move in an industry obsessed with numbers. But how did Sony actually build it? The answer lies in a radical architecture change called Starvis 2. In the next section, we're going to dive into the literal layers of this chip to see how they flipped the entire world of sensor design upside down to make this possible. It's a journey into the sub-micron level, where light becomes data. And it all starts with a technique called back-illumination. Let's see how they moved the wiring to clear the path for light. For decades, image sensors were built like a sandwich with the wiring on top. This meant that light had to navigate through a metallic jungle of circuits before it could ever reach the light-sensitive photodiodes. This front-illuminated design was inefficient. A huge portion of the light was simply reflected away or absorbed by the wires. To fix this, Sony engineers did something that sounds simple but is incredibly difficult to manufacture. They flipped the sensor over. This is back-illuminated technology, or BSI. By putting the circuitry behind the photodiodes, the light has a completely clear path. In the IMX785, this architecture is refined into what Sony calls Starvis 2. Starvis 2 isn't just about flipping the chip, it's about the depth of the photodiodes. Because the IMX785 has such a large pixel pitch, those photodiodes can be significantly deeper, allowing them to capture photons that would normally pass right through a thinner sensor. This is especially critical for near-infrared light, which has a longer wavelength and tends to penetrate deeper into the silicon. The IMX785 is essentially a photon trap, designed to ensure that once light enters, it never leaves without being counted. The result is a sensor with staggering sensitivity. It can see in environments that would look pitch black to a standard camera, all without needing to ramp up the digital gain and introduce that dreaded noise. But there's another clever engineering trick inside the IMX785. The stacked design. Instead of trying to cram the processing logic onto the same layer as the pixels, Sony stacks the logic chip directly underneath the pixel chip. These layers are connected by through-silicon vias, microscopic vertical wires that allow for massive data bandwidth. This means the IMX785 can read out all 5.12 megapixels almost instantaneously, eliminating the rolling shutter effect. This stacking also allows Sony to include dedicated noise reduction circuitry right on the chip, processing the signal at the source before it ever reaches the rest of the camera system. Think of the engineering required here. We're talking about aligning two different silicon wafers with nanometer precision, and then bonding them together so they act as a single unit. It's a triumph of modern manufacturing. By separating the light gathering from the processing, each layer can be optimized for its specific job. The pixel layer is optimized for pure physics, while the logic layer is optimized for pure speed. This specialization is why the IMX785 can achieve such a high dynamic range. It has the brain power to manage the massive amount of light data that its eyes are collecting every millisecond. So we have the 2.9 micrometer pixels, the back-illuminated StarVis 2 architecture, and the stacked logic layer. When you combine these, you get something that defies the traditional rules of photography. But why does this matter for the future? Why is the industry starting to move away from the megapixel race and toward this new era of photon efficiency? The answer lies in how we use cameras today, not just for taking pretty photos, but for allowing machines to see the world with more clarity than any human eye ever could. For 20 years, the camera industry was stuck in a numbers game. Higher megapixels meant better marketing, even if it meant worse actual performance in difficult lighting. But we finally hit a physical wall. You can't make a pixel smaller than the wavelength of light itself without running into the laws of diffraction. Once your pixels get too small, the light starts to blur across multiple pixels, and you actually lose detail. Sony's IMX785 is a statement that the era of more is over, and the era of better has begun. By using fewer, larger pixels, they are maximizing the quality of every single bit of data. This shift is being driven by industries where failure isn't an option. Think of autonomous vehicles. A car doesn't need a 100 megapixel photo of a stop sign. It needs to be able to see that stop sign in a blizzard at midnight with zero motion blur. In these scenarios, the 2.9 micrometer pixel pitch is a lifesaver. It provides the high-speed readout and low light sensitivity required to make split-second decisions that keep people safe. The same applies to industrial automation and security. When you're inspecting parts on a high-speed assembly line or monitoring a dark perimeter, photon efficiency is the only metric that truly matters. As this technology trickles down, we're going to see a change in how our personal devices work. Instead of bragging about resolution, the next generation of high-end cameras will brag about their full well capacity and quantum efficiency. We are moving towards computational sensors, chips that don't just capture light, but understand the physics of that light in real time. The IMX785 is one of the first true examples of this philosophy in action. It's a future where your camera doesn't just take a picture of what's there, but uses its massive pixel wells to reconstruct a perfect map of the environment, regardless of the lighting conditions. The engineering behind the IMX785 reminds us that sometimes the most advanced solution is to go back to the basics of physics. By respecting the size of a photon and the limits of silicon, Sony created something truly revolutionary. It's a masterclass in compromise. They gave up the high megapixel count to gain something far more valuable, the ability to see the world with absolute fidelity. And as we continue to push the boundaries of what machines can do, sensors like this will be the eyes that lead the way, turning the invisible into the visible. Next time you see a camera spec sheet, don't just look for the biggest number. Look for the pixel pitch. Look for the architecture. Because as the IMX785 proves, the most powerful images often come from the fewest pixels. The engineering is hidden, but the results are undeniable. We've mastered the art of catching light, and we're just getting started. The next time you're out at night and you wonder how a camera can see what you can't, you'll know exactly what's happening inside that silicon, one massive, perfectly designed pixel at a time.